All right, so yesterday we talked about degrees, and now we're going to talk a little bit about radian measure. We use radian measure quite a bit in this class, sometimes more than degrees, and you're going to see why, because it fits our circles a little bit better when we get to our unit circle in a little bit. So what is a radian? A radian is if I take a radius of a circle, like right here, and I wrap it around the circumference of the circle. The angle that is formed is called 1 radian. So if my radius matches this arc length, the angle in the middle is 1 radian. Now if I take that radius and I start wrapping it around my circle multiple times, it actually fits around the circle 6.28 approximately times. What's 6.8 divided by 2? 6.28 divided by 2. 3.14, and what is 3.14? Pi. So what ends up happening is we can fit 3.14 radians halfway around and another 3.14 radians for the other half. So one full rotation is 2 times 3.14, 2 pi radians, or half a rotation is pi radians. Now we know half a rotation is 180 degrees. That's the conversion that we're going to use. So pi radians, which we usually don't see the label with it, and might just see a pi, 180 degrees, those are equivalent measures. There are two ways of saying just a half rotation around a circle. If you want to convert degrees to radians, we multiply by pi over 180. If you want to multiply the other way, radians to degrees, we use 180 over pi. And that just gets the unit we want to cancel. Okay. So first thing we're going to do, you're going to need your calculator for it. We're just going to take a few degrees and radians and just practice converting. And then in a little bit, I'll get you a circle and we'll fill out all the important angles that you guys need to know. Okay. All right, so make sure you have those two conversions written down, pi over 180, 180 over pi. Okay. We're just going to do a few of these. We're going to kind of pop around here a little bit. Let's say I want to take 30 degrees and I want to convert it from degrees to radians. So we're going to multiply by 2 equivalent units. Pi radians, 180 degrees. Now, this degree right now, you can imagine it's on the top of a fraction, which means if you're not sure what to multiply, you want to make sure the degree unit is going to cancel. So we know 180 degrees needs to go on the bottom, which means pi radians is going to go on top. Okay, it's just like multiplying by 1 because those are equal. We're going to multiply straight across 30 pi over 180, which at this point you could get a decimal if you wanted to, but radians, we typically like exact answers. Like when you do Math Excel, it'll say give an exact answer in terms of pi, which means we're going to leave the pi there. And we're just going to reduce the numbers in front of the pi, so 30 over 180. So if you want, you can use your calculator for this. Alpha y equals, set up a fraction, put 30 over 180 in, and then just hit enter, and it'll reduce it automatically for you. And you should see 1/6. Yeah? Okay. So we could write 1 pi over 6, or how we typically see it written is just pi over 6 radians is equal to 30 degrees. Okay, let's do one more of those. Negative 225. Multiply by pi over 180. We're just going to multiply straight across. Again, the degrees are going to cancel. So it'll be negative 225 pi over 180. And then we just reduce, put that 225 over 180 in your calculator, enter, and you should see negative 5/4 or 5/4 if you didn't put the negative in. So negative 5 pi over 4 radians is equivalent. Make sense? Okay. Converting the other way, again, we'll just do a couple of these. Let's do like pi over 3. If I have radians, pi over 3, we multiply by, this time, that pi is on top, which is a big clue. My radian unit is what we want to cancel, so I'm going to put the pi on the bottom, 180 degrees on top. If I multiply straight across, it's 180 pi over 3 pi The pi's cancel, and then you can do 180 divided by 3 gives you 60 degrees. Okay. Last one, let's convert 1. If you don't see a degree symbol, you are to assume that something is a radian. So that 1 means 1 radian. Doesn't always have to have a pi in it. Because it's a radian, we multiply by 180 over pi. Okay. And that would give me 180 over pi. Usually we don't write degrees like this in terms of pi. We usually give a decimal approximation. So go ahead and divide that in your calculator. And you should get 57.3. Does that sound right? Double check me. 57 point, what's the decimal? 3? Yeah, approximately. Okay. So if you think about that previous picture I showed you with the circle and the radius kind of wrapped around the edge, that angle that's forming when we see 1 radian is about 57 degrees. So what's a radian? It's about 57 degrees. Okay. Questions? Cool. All right, I have unit circles for you. We're not going to get too much into the unit circle yet. When we get to section 5.3, that's where we'll start putting all like the sines and cosines. You guys remember doing that before. Today we're just going to focus on the angles, all the degrees and radians that are going to be really important for us this semester. The unit circle is going to be your best friend in this class. We're going to use it every day, all the time. It's like the periodic table of elements in chemistry. This is our periodic table of elements. 1, 2, 3, 4. All right. Everybody got one? Okay, so we're going to get the degrees and the radians on here. Let's start with, we did this yesterday when we were practicing drawing our angles in standard form. When we were talking about our unit circle, all of our angles are going to be in standard form, which means the rotation is going to start on the positive side of the x-axis, so that's our 0 degrees. And then we're going to rotate counterclockwise, so I'm going to rotate up. If I do a quarter turn, so if I get to the y-axis, how many degrees is that? 90. If I do another quarter turn, I end up at 180 at the bottom, 270. And then if I rotate back where I started, how many degrees is that? 360. Okay, the other degree measures that are on here come from your special triangles in geometry, your 30, 60, 90 triangles and your 45, 45, 90 triangles, which we'll review those a little bit in the next section. So 30, 45, and 60 are those special angles. And you'll notice there's kind of a pattern here. We're counting by 30, then 15, 15, 30. It's going to go the same all the way around your circle. Increase by 30, 15, 15, 30 to get to 360. Okay, so if I take 90, increase by 30, it's 120, then 15, 135, 15, 150, 30 takes me to 180. 30 is 210, then 225, and 240 when I add 15. Another 30 gives me to 270. And then one more time, 30, 15, 15, and then 30 takes me back to 360. So those are all of our degree measures that we're going to be using on our unit circle. Good there? Okay, so now the radians we want to add to this also. So we're also going to have 0 radians where we have 0 degrees. Our rotations are going to start in the same place. If you do a full rotation, we just talked about this, how many radians is that? 2 pi is a full rotation. And what's half a rotation? Pi. Okay, there were a couple other ones that we had in the examples that we just did. 30 degrees we converted to pi over 6. 60 degrees we got when we converted pi over 3. So we had those answers in our notes already. 225 we actually did negative 225 was negative 5 pi over 4. 225 is positive 5 pi over 4. So we kind of know some of those. If you're halfway between 0 and pi, where are you at? Pi divided by 2. That's 90 degrees, halfway between 0 and pi. If you're halfway between pi and 2 pi, where are you? 1.5 pi, or 3 pi over 2. Do you guys see how the fractions make sense with the rotations here a little bit? So we want to think of our picture as just like the top half of this circle. The top half of the circle is a hole. And 1 pi represents the whole, 0 pi represents nothing. Pi over 2 represents half of my picture. If you remember that pi over 6, 30 degrees, is 1/6 of the way to pi, it's going to give you the majority of the rest of these radian measures on here. Every 30-degree rotation is pi over 6 radians that we can add on. Okay, so I have 1 pi over 6 when I'm at 30. 2 pi over 6 when I'm at 60, and 2, 6 reduces to 1/3. 3 pi over 6 if I'm at 90, and that's 1/2. So this guy's my next one. That's 4/6. What does 4/6 reduce to? 2/3. So put 2 pi over 3 here. Then 1/50 is my next 30-degree rotation. So now I'm at how many 6? This was 4/6. 5/6. Does that reduce? Nope. So let's get those two on there. And then we're going to keep doing the same thing. We're just going to keep adding 1/6 every 30 degrees. So 5/6 plus 1/6 is 6/6. 180 degrees. That takes me to pi. We got that one already. Add another 30 degrees to 210 would be 7/6. Another 30 degrees to get me to 240 would be 8/6. What does that reduce to? 4/3. Add another 30 degrees to get to 270. That's 9/6, which is 3/2. We've already got that one. Another 30 degrees to get to 300 is 10/6. What does that reduce to? 5 pi over 3. To 330, it would be 11/6, which does not reduce. And then to get to 360, we're back to 12/6, which is our 2 pi that we've already got. Now, the only ones that you're missing now, once you go all the way around with your 6, are the 45-degree increments. 45 degrees, that rotation is what fraction of 180? 45 is what fraction of 180? 1/4. If you can remember that, 45 degrees is 1/4, or pi over 4. All you have to do is every 45 degrees add a 4th. So 45 degrees is 1/4. 90 degrees is 2/4. We already had that one. So this guy's going to be 3/4. And then 180 is 4/4, which is pi. We've already got it. So 225 is 5/4. We've already got that one. 270 is 6/4. We've already got that one. 315 is 7/4. And then 2 pi takes me back to, or 8/4 takes me back to 2 pi, my full rotation. Do you see why the fractions make sense here? Honestly, if you learned both of these at the very beginning, like back in, I don't know, whenever you started angles, like 6th grade, radians are more logical when we look at a circle because you can see the fractions. When you really think about it, degrees are kind of like these arbitrary numbers. We just know them because we're used to them, but they really don't make a whole lot of sense when we start talking about circles. But in trig, we use circles a lot. So the fractions are going to be a lot more reasonable, okay, when we see our problems. It should be nicer to use, okay? Where are my sophomores in here? I know I have a few, right? Okay. Tomorrow, we're not going to do a new lesson, so you don't have a video to watch. The only thing you're going to be missing is we're going to play a little game practicing where these are located on here. So if you're going to miss class tomorrow, if you're in one of the career techs or you're a sophomore, just kind of look over your angles and your radians, make sure you know where something's located. Like if I said 7 pi over 6, should take you 2 seconds to be able to point to that location on the unit circle. That's kind of our goal for tomorrow, is just to get used to where these are located, because once we start adding coordinates on here and sines and cosines, being able to locate it quickly is going to make your life a whole lot easier this semester. Okay? All right, cool. All right, you can tuck those away, but hang on to them. Like I said, we're going to be using those. We'll add to them in a couple sections. Keep them in your notebook. All right. So now we just got a few little extra. Yeah? You have early dismissal? Yep, go ahead. So we actually just have a few extra little like formulas and tidbits we're going to kind of add on to wrap up the section here. So things that they add in here: arc length formula, area of a sector formula. Write these down. You probably did, if not these, a version of these in geometry. Arc length is part of your circumference, and area of a sector is the area of a pie piece. If we're talking about our circles. S is the arc length. R, of course, is radius. A is area. And theta, bye, is an angle, a central angle. But you've got to be careful with these formulas. There's different versions of them when you Google them. These two specific versions are written so that the angle must be in radians. Okay, so if you use these formulas, which really are the easier version of the formula, you must make sure your angle is in radians first before you plug it in. Okay, so quick example of how you would use these. I just drew kind of a sketch of a circle here for you. It says find the arc length and the area of a sector created by an angle of 52 degrees in a circle that has a radius of 7. So if you want to make a sketch from the center of your circle out, and if I have a choice, I'm always going to make my angle start there because that's what our standard position angles look like. Radius is 7, angle of rotation 52 degrees. So we're trying to find two things. We're trying to find the arc length, which is the distance between the initial and the terminal side of the angles where it intersects the circle, and then that's our arc length, and then we're trying to also find the area of that kind of pie piece I've created. That's the area of my sector. Before I do either of those, I need to take 52 degrees, my angle, and I need to convert it to a radian measure. So how do we convert degrees to radians? What do we multiply by? Pi over 180. We know the degrees are going to cancel, and this isn't my final answer anyway, so I'm not super concerned about reducing it. I'm just going to leave it like this, 52 pi over 180. Okay. Now I want arc length first, so that's just S equals r theta, where r is my radius, 7, and theta is 52 pi over 180. And then you just type it in. A decimal would be appropriate here. You round to, whatever you need to if you're doing your math Excel. So 7 times 52 times pi divided by 180, get about 6.35. This is a distance. We would need to label it. We don't have a unit here, so I'm just going to say units. Okay. Other thing we need to find here is area of the sector. Area is 1/2 radius squared times theta, again, where theta is a radian. So 1/2, 7 squared, and again, I'm just going to use 52 pi over 180. Type it in your calculator, get that decimal. Ooh, that's not right. Did I type that in right? Maybe I did. Do you get 22.2? Okay. I think I typed it in wrong third period and nobody called me out on it. Make sure, because it's an area, you label it units squared. Okay. Questions there? We okay? Good? Okay. So a application of our arc length formula is latitude and longitude. You can think of two cities that are directly above each other, at least for ease of calculation purposes, on the Earth as that actual distance is an arc length, right? Because the Earth is curved, okay? So if we wanted to know, for example, how far apart Chicago and Pensacola, Florida are, assuming they're directly above one another on the latitude lines or the longitude lines, we can take their latitude and we can find the difference in them. The difference in the latitudes will give us a central angle. And now do you see how that kind of looks like the arc length picture on the previous slide? We can find S there, and that's going to give me the distance between the cities. So what you need to write down your two latitudes here, Chicago and Pensacola, Florida. And then they're also telling us that we are supposed to use the radius of the Earth is about 3,960 miles. So I have my radius if I'm doing my arc length formula. What I don't have is my angle, and we'll get the angle in a degree first, and then we'll put it in a radian before we actually use our formula. Again, the difference in the latitudes is going to be the angle between those two cities. So I need to subtract them, and we're just going to do like old school subtraction here. 41 degrees, 51 minutes minus 30 degrees, 25 minutes. Or using that degree, minute, second notation we talked about yesterday. Subtracting, you guys can just subtract the minutes and the degrees from each other. Like what's 51 minutes minus 25 minutes? 26 minutes. And what's 41 degrees minus 30 degrees? 11 degrees. So that is my angle theta. The only problem with theta now is it's a degree, not a radian. So here's how we're going to put it in our formula. I'm going to use S equals, I'm going to put my R there, 3,960. If I wanted to type in my calculator 11 degrees and 26 minutes, I would do 11 plus 26 minutes is what fraction of a degree? We did that yesterday. 26 minutes is what fraction of a degree? 26 60ths. Okay, so that's that 11 degrees, 26 minutes, and then we know that number has to be multiplied by pi over 180, right, to do that conversion. You can just type that whole thing in your calculator if you want all at once here. And again, a decimal would be appropriate for your answer. Let's see. 790.22. Yeah. What would I label this? My distance is measured in what here? Miles. Yeah. Okay. You're going to see one like that on Math Excel. Do you have questions there on that one? Okay. Last two problems today are again kind of applications of radians, which is why they're showing up in this section. They have to do with linear and angular speed, and you need to write down these three little, I'm going to call them mini formulas. They're not too terrible. So V stands for linear speed, and W, it's like a cursive W there, stands for angular speed. Linear speed is if you are traveling in a line, like miles per hour. That is a linear speed. Angular speed is if you are traveling in a circle. So a lot of times we talk about like revolutions per minute, RPMs, if you've heard something like that before. We talk about like how fast a lawnmower blade spins, something like that. That would be an angular speed. And then the third formula, V equals RW, is the relationship between the two. If you want to convert angular speed to linear speed, you just multiply by R, the radius that it's turning around. Oh, My watch is talking to me about linear and angular speed. How convenient. S is distance. I'll label some of these for you. T is a time unit. My theta here, again, is a radian. T is time. And then R, of course, is a radius. And V is linear speed, W is angular speed. So that's what all of our variables stand for. Okay, so we're going to do two examples with this. The first one, we're going to look at a model plane that's spinning in a circle, and we want to find its angular speed and its linear speed. Okay, so this one says a model plane is attached to a swivel so that it flies in a circular path. Find the linear and angular speed of the plane if it's attached to a 10-foot wire, assuming it's flying at 18 revolutions per minute. Okay, so here's a little picture of this. So we've got like this post that a wire, a 10-foot wire, is attached to, and at the end of it, there's this plane. Okay, now if the plane tries to fly because it's attached to this wire, it's not going to be able to go straight. It's just going to go in this circular path over and over again. Okay, so we want to find angular speed and linear speed. Now it's already traveling in a circle, so angular speed is the closest to what we have already. So I'm going to do that first. Calculate my angular speed W. To get that, I need the radians that it travels divided by the time that it takes to travel that far. Now, we know it travels 18 revolutions per minute. A revolution is not a radian. A revolution, a full turn, is how many radians? 2 pi, okay? So every revolution, it's traveling 2 pi radians. So how many radians does it travel? It travels 18 times 2 pi. That's my theta. And then how much time does it take to travel those 18 revolutions? 1 minute. 18 revolutions per minute. So 36 pi. And you can just leave it like that. We would label it radians per minute. It's always radians per whatever our time unit is. Here it's minutes. That's your angular speed. Now the other thing I need is linear speed. Linear speed is going to be how fast this plane flies if it all of a sudden gets detached from the post and is able to fly straight instead of being stuck in this circular pattern. To get linear speed, if you already have angular speed, it's just R times W. And my radius here is 10. My angular speed was 36 pi. So the exact answer here is 360 pi, but we wouldn't say something travels that fast in a line. We would get the decimal again, approximation. So 360 times pi gives me approximately 1,131 if I round to the nearest whole number. And then that's a distance divided by a time. The distance here is measured in feet, because that's how long the wire was, divided by the time unit we have, which was minutes. So feet per minute, 1,131 feet per minute is how far that's actually traveling if it were allowed to go in a line. Okay. Questions there? All right. Last problem is similar to this, but it's gonna we're gonna have a little converting in it. It's gonna kind of look like what's it called in chemistry? Stoichiometry. The big fractions. Do you guys know what I'm talking about? Anybody take chemistry? Yeah, it's gonna look like that. Okay. So bicycle wheels are 30 inches in diameter. The angular speed of the wheels is 11 radians per second. Find the speed of the bicycle in miles per hour. All right, so what do I have in this problem? I have angular speed. Let's write that down. My W is 11 radians per 1 second. And labels are going to be important here. We're going to have a lot of different units, so I'm going to make sure I label. 30 inches in diameter. Diameter doesn't help me too much, but it helps me get the radius, right? What's the radius going to be? 15 what? Inches. Okay, again, the labels are important. We are trying to find the speed that the bike's traveling in a straight line, which is linear speed, V. And how do I get linear speed? If I have angular speed, I just multiply it by the radius. So my radius, 15, times my angular speed, 11 radians per 1 second, and that 15 again was inches, if I can squeeze it in there. There we go. Multiply them together. 15 times 11, 165. And what's my unit? It's a distance divided by a time. The distance here is inches. The time is seconds. Okay, so the bike is traveling, has a linear speed of 165 inches per second. That is not what the question is asking for, though. It wants the speed in miles per hour. So now comes the conversions. We need to convert seconds to hours and inches to miles, and you can do them in either order, doesn't matter. Let's do the inches to miles first. Okay, so inches I can first convert to what? What's the next unit? Feet. How many inches are in a foot? 12, right? Okay, so inches already is in the numerator, which means if I want that unit to cancel, I need to put it in the denominator. 12 inches is equivalent to 1 foot. Whatever you're multiplying by, you want to make sure each of these fractions you set up are equivalent measurements. 1 foot is the same thing as 12 inches. It's like multiplying by 1, but we place things in a certain position so it cancels out the unit I don't want. And then if I have feet, I can convert to miles, right? How many feet are in a mile? $5,280. That's it. 5 people went to a party and ate nothing. 5 tomatoes. However you want to remember it. All right, so now I've got my miles. Then I want to convert seconds to hours. So this is kind of like what we did yesterday with the degrees, minutes, seconds, right? Seconds I can first convert to what? What's the next biggest unit? Seconds to minutes. How many seconds are in a minute? 60. And seconds right now is on the bottom, so I know to put seconds on top. 60 seconds, 1 minute. And then minutes I can convert to hours. Again, 60 minutes, 1 hour. Minutes got to go on the top so it cancels. So now any units that are in opposite positions are going to cancel, which means inches are gone, feet are gone, seconds are gone, minutes are gone, and I am left with miles on the top and hours on the bottom, which is what we want, miles per hour. Multiply straight across. 165 times 60 times 60 on top gives me 594,000. 12 times 5280 on the bottom is 63360. And then we divide. And we get approximately, actually, it's exactly 9.375. And it was in miles per hour, which would be reasonable for the speed of a bike, right? If we got like this kid is traveling at 68 miles per hour, it's probably wrong because he's on a bike, and that would be crazy. Be on the expressway with everybody else, right? So we want to check our answer, make sure it's reasonable at the end, okay? That is it for 5-1. That's everything. We got it, okay? Any questions for me? All right, so if you're not going to be in here tomorrow, there's no video, there's no notes. We're just going to play a little game with the degrees and radians, and then everybody's going to have some time to work on Math Excel in class tomorrow is the plan. Math Excel 5-1, your first Math Excel is due Thursday night. So again, maybe a New Year's resolution, work on our Math Excel in advance, not the day it's due. Send me questions if you have them in the meantime. These are options you have, right? All right, I'll do cell phone lotto, and the last few minutes are yours.